In this lecture, we're going to go back in time to when we had something called combinatorial topology. Well, you still have it, but as we said, it is outdated. So let's give a bit of a history lesson. So in the old days, maybe like right at around 1900, plus or minus 10, 20 years, and for a while, people did something called combinatorial topology. And you will see why it has that particular name. Nowadays, it's not something that we do because we have a better way to do it. So that evolved into something that we now call algebraic topology. And if you open up a modern textbook on topology, you will probably not see this discussed that much. But maybe from a historical perspective, it's nice to learn it because sometimes when you see the modern treatment of something, you do not appreciate what is being done because you do not see the historical development of those ideas. So what is combinatorial topology? Basically, the way it works is that you start with something that's combinatorial. So you have a finite amount of data with a combinatorial structure. And then from that one, you reconstruct a topological space. The modern approachment is to completely skip this and just go to the topological space. But in the old days, that's what you would do. You would begin with a combinatorial structure. So by combinatorial, I mean something that is described by a finite collection of sets that satisfy certain properties. And then from there, you can recreate a topological space. And there's this issue, of course, that you can have different combinatorial structures that lead to the same topological space. So in other words, topological spaces that are homeomorphic. So this is sometimes an annoyance, but basically you go from here to there. So that's why it's called combinatorial topology. You go from combinatorics to topology. And we're not going to completely say how to do that. What I wanted to do today in this lecture is I just wanted to focus on the combinatorics. We're not going to discuss how you go from combinatorics into the topological space because that's a bit more outdated. But I just wanted to focus on this first part. And the combinatorial structure that you're using is called the simplicial complex. And what it is simply a generalization of a discrete graph. So perhaps you recall that we talked about topological graphs and discrete graphs, and the distinction is that a topological graph is the topological space, and a discrete graph is a combinatorial representation of that topological space. And a simplicial complex is just a higher dimensional analog of that. It's the same idea. And so in the old days, so also let's say this, so in the old days, homology, so the homology groups, was defined on the simplicial complex. Not on the topological space. So this is the old approach to homology. Before you create a topological space, you begin with a combinatorial structure called a simplicial complex. And then homology is defined on that simplicial complex. And in fact, the motivation for homology was a way to distinguish between different simplicial complexes. Because as we remarked, sometimes different combinatorial structures lead to the same topological space. And Poincaré had this observation that if you define these things called homology groups, then they are isomorphic if the topological spaces are homeomorphic. So even though the combinatorial structures could be very different, in the end they become the same if you're describing the same space. So you can say that was one of the reasons for why homology was introduced. It was a topological invariant that was there to distinguish between the different simplicial complexes, so you know if you have the same space or something else. Now, as we remarked, nowadays we do not do homology like this. The way we defined homology in the previous class is a little bit different. We immediately, so this is what we do nowadays, we immediately, so defining homology directly for a topological space is the modern approach. We just immediately start with a topological space. And you see, this is a lot better because clearly it is invariant for combinatorial structures because it does not even use them. But it's also better in the sense because if you can have some kind of, let's say, a more bizarre or a more difficult topological space that cannot be described as a simplicial complex, and our previous definition that we talked about last class, it still applies. It applies to any topological space. We do not have to limit ourselves to the kind of topological spaces that we are allowed to use. So as you can see, working with the topological space directly is a much better way to do it. But we'll discuss how you define the homology by ignoring the topological space and by only looking at this thing called the simplicial complex. So let's give a disclaimer for what we're about to do. So disclaimer. So there is no topology. Nothing we're going to be doing today will use any kind of topology. So in theory, we can explain all of this to like a talented high schooler. It's very elementary. We are forgetting about topology completely. So everything that we've talked about in the previous lecture, you want to maybe forget about it for the most part. But it is inspired by topology. So today we will be drawing pictures, but the pictures is more of a motivation for what we're trying to say. The actual definitions have nothing to do with topology, so just keep that in mind. So when you're reviewing this or when you're working on homework problems, and then you're wondering why are the pictures that like where are those pictures coming from if they're not a part of the definition, you need to understand they're not part of the definition. The definition is going to be completely discrete. There's going to be no topology on it whatsoever. The pictures is sort of a way to visualize what the definitions are trying to say. So with that disclaimer, let's give the definition of a simplicial complex. This is definition. A simplicial complex, let's call it script K, that's a script K, is a finite collection of finite sets. Actually, there are some people who allow it to be an infinite collection of finite sets, but let's not even worry about that. And then we would say that if sigma belongs to K, we call sigma a simplex. So we're going to call it a simplex. But of course, this is just a set. This is a set. So K is a collection of sets. This is actually very common math notation. Is like if you have a lowercase letter, that's an element from somewhere. If you have an uppercase letter, that's usually a set. And if you have, let's say, a decorated uppercase cursive letter, then that you can call that a set of sets, but you can call it a family of sets or a collection of sets. So this is sort of very common progression of letters that we use in mathematics. So that's why we call it a cursive K, to indicate that it is sort of a set of sets. And when we're choosing an element in K, we're not calling it by an uppercase letter, and we're not even calling it an element, we're just calling it a simplex. Of course, it does not matter how you call it. It's really about the way you want to visualize it. So we're going to visualize it as a simplex, but of course, it's just an element in K. It's just a finite set and nothing more. So we call it a simplex. And let's also say that if the cardinality of sigma is equal to n plus 1, or maybe let's say we call it n. So that's how many elements are in sigma. Then we say the dimension of sigma is 1 less, n minus 1. So you can call this an n minus 1 simplex, an n minus 1 dimensional simplex. Of course, it does not make sense to say that a finite set of points has dimension n minus 1. It will make sense if you visualize sigma as some kind of topological space, and then it will make sense. So these are, of course, just definitions, but I'm trying to sort of explain to you why we call it the way that we do. Of course, the empty set causes funny things to happen. Do we say the dimension of the empty set is -1? Let's not worry about it. I guess some people would say the dimension of the empty set is -infinity, but let's not even go there. And the dimension of your simplicial complex is the maximum of all of the simplices. So you look at all of the simplices that make it up. So these are just the individual sets that are sitting inside the complex. And you take the maximum dimension that you see. So let me give you some examples. So here's like the first example. So a simplicial complex is equal to this. So it's a set. Let's say we put in the empty set. Oh, I forgot to write down the most important property. Kind of rushed that ahead. Though one does not need to, but I think it's better to put this property in. And K has the property. I guess I should have put the property first. That if you have a simplex in the complex, and let's say you have a subset called tau, then tau is also in the complex. This last property is not truly essential, because if K does not have that property, you fill it in with extra sets so it does have the property. Let me give you an example. So K is a set containing the empty set. So we would always have to include the empty set as part of our complex if we want this property to happen, because if anything is in K, then its subset has to be in K. Unless, of course, K is empty itself, but let's not worry about those silly things. Then you have a set containing a symbol A, a set containing a symbol B, and the set containing A and B together. So why is this a simplicial complex? Well, you can check that anything you choose in K, let's say you choose sigma, you can see that its subsets are included in here. So you have A and the empty set, and you have B and the empty set. And if you choose this one, its subsets are just itself and the empty set. And you can kind of go through this, and you can see that this satisfies the definition of a simplicial complex. So this is you can say the formal definition. But what we were saying is that this is supposed to represent, you can say this is the intuitive picture for what it's supposed to represent. But the actual definition will be this and nothing more. So this picture is not really part of the definition. So you're going to, so you have, you kind of ignore the empty set, but you have A and B. So you have A over here, and you have B over there. So you have A and B, and then you can see that A and B are connected. So you connect them by a line. So this simplicial complex is supposed to represent, this is supposed to represent an interval. And of course, this interval is homeomorphic to delta 1, right? The one-dimensional simplex that we talked about. But this is like an actual topological space. But that's what it's supposed to represent. The points in between A and B, they're not part of the definition of K, but you sort of like fill them in, and then you get a topological space out of that. So this process of going from there to there, that's called, you can call that the, so they called it, in the old days, they called that the geometric realization of the complex. It's a way to geometrically realize it as something very specific. I'm not a fan of calling it the geometric realization. Maybe calling it the topological realization makes more sense here. But because we do not care about how far apart A and B are, that's why geometric is not really the best way to put it. But that's what they called it in the old days. So we'll just call it the geometric realization. And we're not going to discuss how to do that because we do not need to know how to do that. But you can find some books on topology. In fact, Moncrief talks about this. So there's a book by Moncrief. There's a book called Elements of Algebraic Topology by Moncrief. So Moncrief has a number of books. So we all know him for his topology book, but he has another topology book. And the way Moncrief begins the book is he starts the book completely about simplicial complexes. And he dedicates a very big part of the book to simplicial complexes, how you can geometrically realize them as topological spaces. He defines homology. He proves many theorems on homology. And then the book progresses, and he gets to the point where he defines topology, where he defines homology on a topological space by just skipping the whole simplicial complex approach. So that's the modern way to do it. So he actually starts with combinatorial topology, and then he evolves into algebraic topology later in the book. But we're not going to do that because it's just not really necessary, but it's kind of nice to know where this comes from. Let me give you another example. So another example would be, you can have a simplicial complex that, let's say, goes like this. You have the empty set. Well, let's not even write down the empty set. Let's write down AB. You write down AC, and then you write down BC. Now, recall what I said. The property of a simplicial complex, that if you have a set, its subsets are part of the simplicial complex. What we often do is we like to be lazy in mathematics, so we do not even bother to write that down. So we just understand it from the context. But if you really wanted to be careful, you would say, of course, you have to contain, even though you're not writing it down, you have to contain A, you have to contain B, and for this one, you have to contain C. There's no need to write down A again. You already have that. And you also include the empty set, though maybe it's never going to be part of the picture, but this is sort of the way you write it down. Okay, so again, this is, as we said, this is the formal definition. And now let's try to get what is known as the geometric realization of that picture. So how would you guess this looks like? Well, you have A, B, and C. You have 3 points, so you draw 3 points, A, B, and C. And then you see that A and B are connected together. So as you can see, this is kind of like a graph. This is what we're saying. This is a generalization of a graph. So A and B are connected to each other, so you would connect them. B and C are connected to each other, so you would connect them. So maybe before I go on, so when I talk about the geometric realization, it's not as simple as you think it means. Because if you, let's say, put A, B, and C in a straight line, and you go from A to B, you go from B to C, how do you connect A and C? If you draw a line that sort of goes above them to connect it, then the issue would be is that you're kind of going over the same line twice. And then it looks like you're getting something that's a straight line. And that's not what you want. So you really have to configure A, B, and C in this way and not in a straight line. So that's why it's a bit unclear what we mean by a geometric realization. You cannot just take these points, you position them, and you connect them by lines. What if the lines happen to intersect or things like that? You do not want that extra intersection point to be part of your topological space. So it's a bit unclear how you actually geometrically realize it. And it takes work to explain how to do that, but let's not really worry about that. So you have A, B, and C, and then you would connect A and C together. And that's a triangle, right? That's a triangle. And this triangle is homeomorphic to the circle. So we would say that the geometric realization of that is something that's homeomorphic to the circle. So in combinatorial topology books, the geometric realization would always consist of straight lines. So it would be some triangle, but then the triangle is homeomorphic to the circle. Okay, so let's give some other definitions. Maybe we make one that's, well, before I go on, what if you have a complex K prime and it's rather given by the set containing A, B, C. A, B, C taken together. So that's your simplex. So this is your simplex. Of course, we're sloppy. We do not write down the subsets, but you do have the subsets. You have A, B, and so on, all the way up to the empty set. So how would you turn that into a picture? Well, the way you would do it is you have the points, have A, B, and C, and you fill it in just like before. And you say, what's the difference? Well, the difference is that A, B, and C have to be taken together in one set. So you need to find a set that contains A, B, and C together. These lines do not contain all three of them. And the one that does it is the filled in piece. That's why we say the dimension of the simplex ABC is equal to 2. It's 1 less. You see, you have 3 elements, but the dimension of it is equal to 2. Because we're not talking about the dimension of the simplex. We're talking about the dimension of its geometric realization. You realize it as something that's sitting in some kind of Euclidean space, and then the dimension of that region that you get, you would say, has dimension 2. Because now you have to fill it in. And now you can see that these are actually different topological spaces. This one is homeomorphic to a circle, and this one would be homeomorphic. This one would be homeomorphic to D2, the two-dimensional closed disk. So even though it looks like you're describing the same space, well, to be fair, you're not describing a space, but you turn that simplicial complex, you realize it as a space. So the realized space that you get out of it, they will be different, even though it looks like the two simplicial complexes are the same. Let me give you maybe one more example. Let's say you have a simplicial complex that goes like this. You have ABC, ABD, BCD, and I guess I forgot from one more, ACD. And we're being sloppy. We're not writing down the subsets, but you, of course, have the subsets. So the way you draw the picture is you first draw A, B. You first draw the individual elements that make them up. So you have A, B, C. And now here's the thing that you have to do. The general idea is that as you add, well, let me not do that. No, I do not want to say that. But so let's say we draw D, let's say right over here. So let's see what happens. You have A, B, C. So you're going to connect. So notice that A and B, there's a connection between A and B. There's a connection between B and D. So there's a connection between any two of these. Then you have a connection between A and D, right? Because now you look at subsets of size 2. And you now want to have a connection between C and B. But the problem is you cannot go like this. And you're not allowed to do that because in a simplicial complex, the geometric realization consists of straight lines. They're all going to be realized as geometric simplicial complexes. So now you can go underneath, but to go underneath, you need to go into the third dimension. So then therefore, let's say A, B, and D are located in the two-dimensional plane, and then the C point is like all the way up here. And now you're in three-dimensional space. It's sort of suspended above it. And then you go like this. You go like that. You go like that. And then the D is now going behind it. And now you drew everything that's made out of straight lines. And they do not overlap in any kind of a way. And now you can see that A, B, and C, that would be the face. A, B, and C, that's the face that now holds those three vertices. So then you would have this face over here. And then you have B, D, and C. B, D, and C. That would be the face that holds the other one. Then you have the face that's behind you and the face that's underneath. So this would be a tetrahedron. So this is a tetrahedron. And topologically, that's homeomorphic to the two-dimensional sphere. So that would be the geometric realization of it. But you see, there's this issue, of course, that sometimes you need to go into higher dimensions so that everything fits together properly. And when you have lots of these when you have many of these simplices, sometimes you have to go into higher and higher and higher and higher dimensions. And of course, you then have to present some kind of argument of why you can restructure that configuration in sufficiently high Euclidean space so there's no like self-crossings or anything like that, which takes some work to show. And let me also add this, and be careful, this picture does not include the solid portion inside the tetrahedron. Otherwise, your simplicial complex must include the following set. It will have to include A, B, C, and D. If you were to take this in and you were to include it into your set, then that will represent visually a simplex that contains all four of those vertices. So it will be filled, it will be solidly filled inside as well. You see, you have 4 points and its dimension has to be one less. So it's a three-dimensional, it'll have to be a three-dimensional simplex. So you have to find a three-dimensional simplex, a solid three-dimensional simplex that contains that, and that's all of the stuff inside it as well. And because you're not including this as part of the definition of this K, that means the solid piece inside is not part of K. Okay, so that so this is another example. Okay, so now that we understand the definition of a simplicial complex, and again, let me emphasize this point again, simplicial complex does not have any topology, it has no picture, it does not have any of that. It's just a finite set, it's just a finite collection of finite sets that has the property that if a set is in your collection, then its subsets are in the collection. But that's the definition, but there's a geometric realization of how you interpret what that picture is supposed to say. So now that we've defined what a simplicial complex is, the next thing is to define how you calculate homology of a simplicial complex. Now we're going to define the homology of a simplicial complex. Simplicial complex. And the notation we will use is that if this K represents our simplicial complex, we're going to write Hn of the simplicial complex. That's very similar to the homology of a topological space. So the difference is this is a topological space, and this is, of course, a simplicial complex. So they're different objects. This is topological, this is combinatorial, but you can develop a theory of homology for simplicial complexes. Now, you could put decorations on this. So for instance, if you want to, maybe you can decorate the simplicial complex with like a little triangle to indicate this is the homology of a simplicial complex. But I think there's no need to do that because we can probably distinguish between the two. And this is going to be, maybe I can tell you where we're going with this, is that if putting bars over K denotes the geometric realization, which we never defined. We're not going to use this approach. That's a very classical approach. We're going to do it differently. But in the old days, as we remarked, from a complex, you can recreate a topological space, which they call the geometric realization. So you just basically take those points and you configure them in some Euclidean space of sufficiently high dimension, and then you start drawing in all of the simplices, and you call that the geometric realization. So this is a topological space, whereas the K by itself is just combinatorial. And then it turns out that the homology associated with the simplicial complex and the homology associated with its geometric realization, that the two approaches to homology, they will be isomorphic groups. So last class, we defined the homology of a topological space, and it's going to be inspired, it's going to inspire how we define the homology of a simplicial complex. However, you should understand that this definition will not involve any topology whatsoever. It's going to be combinatorial. So it's inspired by this, and it's inspired by that, but we really are just going to talk about the homology of a simplicial complex. So there's topology is not going to play a role. That's just the motivation for this. Now, maybe to before we write down the definition, let's maybe recall, so it would be helpful to recall how the homology of a topological space is defined before we define the homology of a simplicial complex. Now, you should notice that we're kind of doing it the funny way. Usually people do homology of simplicial, well, historically people did homology of simplicial complexes first, which led to homology of topological spaces. But I think it's now a better way to learn this by starting with the homology of a topological space first and then kind of going backwards in time. So to do this, maybe we can just focus when the dimension is 1, because it's just easier to draw pictures. But I mean, the same kind of definition works in all dimensions. So how is this defined? This is going to be the collection. This is the collection, the set, or the collection. You can say it's the group, because it's going to be a group. So this is the group of all one-dimensional cycles in X that are equivalent in some way. So you have to put an equivalence relation on that, but basically it's the one cycles in X. And what is a one cycle? Well, here's the way you do it. You define delta 1. So this is by definition. So we start our indexing at 0. So these are going to be points in R2, so that the coordinates are non-negative and the coordinates add up to 1. Now, of course, this is homeomorphic to the interval from 0 to 1, but for notational purposes, as we saw, it's convenient to draw it like that instead. So that's called the one-dimensional simplex. And of course, if you talk about n-dimensional cycles, this would just be an n-dimensional simplex. It's just harder to draw. And then we start with paths in X. And usually a path is from the interval from 0 to 1, but we use this homeomorphic space instead. So these will be mappings from the one-dimensional simplex into X. So we do not assume that these mappings are homeomorphisms or anything like that. They're just arbitrary paths in X. So, and what we do is, yeah, so these are paths in X, so you get some kind of path out of this, right? This is like the image. So you're sort of mapping the simplex, right? You're mapping this simplex. You're mapping this into some kind of curve in X. And as we remarked, it's not the image that we care about, it's the actual mapping. Because otherwise, we're going to run into the problem where the same image can be described by lots of different mappings. So we have to be a little bit careful. So we talk about, so a path is a mapping and not the image. So that's what we mean by mappings. And then after that, we define chains. So we define C1 of X. We call these one chains in X. So what is this? This is just a list, right? This is just a finite list of paths. And the way we describe the final list, this is really a formal sum of paths. And the fanciest way to say that is just this is just a free abelian group generated by all paths. So how does a chain look like? Well, if this square represents your topological space, then let's say you have something like this. This is one path. Then you have another path. Then maybe you have a path that goes twice. Like maybe this one kind of transverses twice over itself. We call that the multiplicity of the path. And then we would describe this as the chain consists of F1. This is sort of like your first path. Then you have a second path, and you describe it by a plus or minus sign. So let's say you use negative F2, and then this third path, it's just being repeated twice. So you just put 2 F3, and that's what the chain represents. You write it in some notation, but it's really like a list. And we use additive notation because we do not, there is no notion of first path or second path or anything like that. This is a little bit different from homotopy. When we juxtapose two paths together, we have a first path and a second path. Here, there is no such notion. This is just a formal sum. So it's commutative by its very nature. Or it's commutative almost by definition. And then what we do is so to define a cycle, a one-dimensional cycle, we need to orient. Because without using orientation, this is not going to make any kind of sense. You have to introduce plus or minus numbers. And so let's say let's say this is our space X. And then we have a path that goes like this. And we have to orient it. We have to make a decision of how it moves. And the orientation is arbitrary, but the convention that we're using is we're going like this. So this is the start, and this is the end. So you start by setting the 0th coordinate equal to 1, and then you end by setting the last coordinate equal to 1. So you basically do it in order of the coordinates. So you just go in order of the coordinates, and you just keep on turning each one on. So you first turn this one on, you activate this one, you activate it by setting equal to 1. You go to the next one, you activate it by equal to 1, and so on. And that gives you a notion of an orientation along this path. So by introducing orientation, you can then talk about what it means to be a cycle. So if you have a path going like this, a path going like that, a path going like that, and then another path going like this, then it makes sense to say that is a cycle for the following reason. So C represents that chain. Okay, so let's say the chain is made out of F1 plus F2 plus F3 plus F4. Okay, and let's say the points are, let's say this is X1, X2, X3, 4. Those are the endpoints. Then when we calculate the boundary of the chain, that is equal to, by definition, and this is going to be a little bit abusive, because formally speaking, when you calculate the boundary of a path, which is a one simplex, you're getting a zero simplex, you're getting another simplex. And these simplices, these chains are mappings. They're mappings. They're not actual points. They're mappings of a point into your space. So we're being a little bit abusive here, but we did remark that. So using our abusive notation, which is more convenient, you look at this first path. Well, technically, there is no such thing as a first path. That's the whole point. It's a cycle. But let's say this is F1. And once you have orientation, then you can talk about the beginning and the end. And then you would just write down that it's equal to x2 minus x1. And the next one would be x3 minus x2 plus x4 minus x3, and then x1 minus x4. And now when you do this carefully, you realize it's equal to 0. So you can now talk about what it means to be a cycle. So a cycle, so a one cycle is a one chain with no boundary, right? With no boundary. But with no boundary, what we mean is the boundary, when you apply the boundary operator, you get 0. So we begin with one chains. That's the collection of all such paths. But we're not really interested in all such paths. We want the good paths, the ones that we want to, the ones that will help us understand the topology. And those are the cycles, the ones that basically go around in the loop. So out of all of those chains, we are interested in the cycles. And how do we define the cycles? We calculate its boundary and check if it's equal to 0. But in order to define the boundary and then get that it's equal to 0, we need to orient. That's why the orientation comes up. So even though, as you can see, this is just a formal sum of paths, when we defined the boundary operator, we introduce orientation into it so that we can then talk about what it means to be a cycle. And now we're going to do something very similar with simplicial complexes. So that's what was a quick overview. And now let's say how we do this. So the definition for Hn of k would be similar. Okay? So let's start with would be similar as, maybe I can add as Hn of some topological space. So I want to start with this. So let's define Cn of k. So this is going to be the n chains in the simplicial complex. Now, before we write down the definition, I just want to show you that it has to be different from the topological version, because otherwise, in the topological version, you talk about mapping the n-dimensional simplex into your topological space X. So if you define n chains for a simplicial complex, then you will talk about mapping an n-dimensional simplex into your, but that makes no sense. This is not a topological space. This like you're taking two very different objects and you're combining them together. This is a topological space. This is not. This is just a finite set of points. So you're not going to define the n-dimensional chains as mappings into K. That makes no sense whatsoever. So instead, this is the way you're going to do it. You're going to define the n-dimensional chains as all n-dimensional simplices that already sit within K. That's the distinction. So it's going to be defined as the free abelian group generated by all n-dimensional simplices. Let's call it sigma. So the dimension of a simplex is the cardinality minus 1. This is not a geometric simplex. This is a discrete simplex. It's just a finite set of points. And its dimension, it's the number minus 1. This is a little bit consistent with the notation that we use for the the geometric n-dimensional simplex, because the coordinates, they start counting from 0. So you have n plus 1 coordinates, but the dimension is 1. Okay, so n-dimensional simplices sigma, where sigma is already in K. So that is the distinction. The distinction lies in that when we have a topological space, we consider all mappings of the geometric simplex into your space. And when you have a simplicial complex, this group Cn is defined to be rather than mappings, they're just the simplices, the discrete simplices that already sit within K. That is the difference. You're not mapping anything anymore. You just take those sets as your simplices. And what you want to realize about this is that this is maybe the key observation, is that this is a finitely generated group. There's a finite number of generators. So in topology, the n-dimensional chains of a topological space, that is an infinitely generated abelian group. In fact, the number of generators will be an uncountable number in most cases. So that is an absolutely gigantic group. There's a huge, huge number of these generators. But in the combinatorial setting, there's a finite number of generators. And this will mean that we'll be able to use this combinatorial approach to calculate these groups, because there's like a finite number of generators, something you can actually compute out. So that's the way we define it. Okay, so that's the definition of Cn of a complex. And what we actually need to do, and we're going to change this a little bit, is we talked about orientations, that if we want to talk about cycles and all of that stuff, we need an orientation. So it will not be the free abelian group generated by n-dimensional simplices. We're going to change this a little bit. We'll add a detail that we want these to be oriented simplices. So let's talk about what it means to be oriented. Okay, so I just have to explain to you what I mean by oriented, and then we have our definition. So a simplex is just a finite set. So let's say sigma is ABC, finite set. An orientation, maybe I should say an orientation on sigma is just a word. This is starting to feel a little bit reminiscent when we talked about free groups, but I guess it's nice because things kind of return back again. It's just a word of those elements. So for example, you can have the letters A, B, C, or you can have C, A, B, or so on. So words, right? This is a word, that is a word. So you have to put them in some kind of order, right? You put them in some kind of order, that's where orientation comes in. And then we say two words are equivalent. Maybe what we can do is this. If we interchange two letters, then we change the sign of the word. So, for example, if you have A, B, C, so this is a word, and you interchange these two, then you get BAC, but it's negative BAC. And if you take, let's say, these two, and you interchange them, then you get negative BCA. So that would be positive BCA. So that's what we mean by an orientation. It's you take your set and you put it in some kind of ordering. So I'm trying to define what I mean by an oriented simplex. An oriented simplex, it's you start with a simplex, but instead of writing down what it is as a set, you write it down in some kind of order. And the rule that we're making up here, this is the rule, this is the orientation rule, is that after you write down the word, the rule would be if you write the word, if you were to start swapping the letters, you're going to be swapping around the negative signs for every swap that you do. So that is what we call an oriented simplex. So an oriented simplex is just like a simplex. So an oriented simplex. So an oriented simplex and maybe I can say a discrete simplex because we are talking about finite sets. So an oriented discrete simplex is just the word from the symbols with the plus minus sign interchanging rule. So you write down the letters, and the rule on those letters is that if you were to swap them around, you just keep on changing the signs. So let's just see a picture of this. So we have ABC and we have negative BAC. So let's write down ABC. So you have ABC, A, B, C. So this is your simplex. This is your simplex. Because you have three of them, the dimension is 2. So you have to represent it as a two-dimensional picture. So you're going to go from A to B, and you're going to draw an arrow. The arrow indicates you're going like this, right? From A to B. Then you go from B to C. And then you go from C, you go back to A. It kind of goes in like a circle. You go back to A again. And as you follow these arrows, that gives you an orientation. And then you have to, of course, fill this in. You have to fill this in because this is a two-dimensional simplex. And the way you get the orientation visually is you use your right-hand rule. So you would draw like your thumb. This is your thumb. This is your hand. And you take your right hand, and your thumb is going to be perpendicular to this plane. So it will either point towards you or away from you. So the thumb will point towards you, or you make it go in the opposite direction. And then the way you determine which direction the thumb points is you curl your fingers, and the fingers have to follow this orientation. So if you try doing this yourself, you will notice that your fingers go according to that rule. And so this is supposed to represent this word. I mean, this, like, formally speaking, this does not look like anything. It's just a finite set with this plus or minus rule to it. But the picture here is we want to visualize this as representing this simplex, this geometric simplex, that it's oriented in the way that the side that you see is the side that's facing you, as opposed to away from you. Now look what happens when you write BAC. So when you write BAC, you would write down the points again. So let's say we write down the points again. So these are going to be our points, A, B, C. And now we have B to A. We're going from B to A. So we're going like this, from B to A. And then from A to C, we're going like this. And then from C, we go back to B. And now if you use the right-hand rule, then the face that you see, it's the wrong face. It's the one that's on the other side. So it's basically the same picture as this, but you have to reflect it. You have to flip it over itself to get the other image. So you're seeing the other, it's really the other side of this. And of course, as we remarked over here, that this word and this word have the same orientation, because if you go, so look at this, if you go, so if you have BCA, if you start at B, you go B to C, then C to A to B, you can see that this word over here and that word over there, they visually represent the same simplex with the same side that is facing towards you. So that's how the orientations work. And so the definition of n-chains, they're not the n-dimensional simplices. You have to orient the simplices. So you have to choose some way of orienting them, and it does not matter how you do it, right? You just orient them somehow. You just pick all of the oriented simplices. It's the one that's generated. Okay, so when we do examples, that will make it be a little bit clearer. But what we need next is we need a boundary operator, because when we talk about the homology groups, we're not going to be interested in the n chains themselves. We're going to be interested in the n cycles. So now let's go ahead and define what we mean by an n-dimensional cycle. So before we write down the definition, let us recall the boundary operator from n+1 chains of some topological space to n-dimensional chains of some topological space X. This is what we call the boundary operator. The boundary operator is the operator that defines for us what it means to be a cycle. And the way we do this is, so we pick a chain, an n+1 chain in X, and for simplicity, we can assume it's just a single path, where F is a mapping from the n+1 simplex into X. And the way we define the boundary, this is the way that we do it, is it's a sum, I going from 0 to n, and we take F and we restrict it to the ith face of delta n. And the notes that I gave you for this, this is an abuse of notation. That's the visualization for what we're trying to do. But the actual name of the map is delta I of F. This is the mapping that you get by setting one of the coordinates equal to 0. So delta I of F is a mapping from the n simplex into X, where this applied to a point, what you do is you take the original function and you just take the ith coordinate and you set it equal to 0. So it'll be x0, x1, you have xi minus 1, you set the ith coordinate equal to 0, and then you continue until xn. So that's the way you do it. This is what you call the ith face. It's sometimes denoted like this. The dimension goes down by 1. So that's the way that it works. But often people write it like this as an abuse of notation, because that's like the idea of what's going on, because the ith face of the n+1 simplex is homeomorphic to the n simplex. And then you include the sign, the orientations, they come up over here, -1 to the I. So this is the way that we define it in topology. The way we define it using the combinatorial definition is actually a lot simpler, and is going to be inspired by this. So here's how we do it. So let us define the boundary operator. And I know I previously wrote Cn plus 1. It does not matter. Maybe for the sake of notation, it will look nicer if I write Cn. So we're going to define an operator from n chains into n minus 1 chains. Let's just say what these are. This is the group, the abelian group generated, free abelian group generated by all oriented n simplices in K. And this is going to be the free abelian group generated by all oriented n minus 1 simplices in K. As opposed to topology, where it's mappings from the geometric simplex into your space. But this is the, and of course, if n, the degenerate case, of course, is if this n is equal to 0, then it would not make sense to map it to C -1. In this case, you can just interpret that as the 0 group, but let's not make a big deal about that. Okay, so this is what we have, and now here's the way we do it. So for simplicity, so we're going to pick C. So this is a oriented simplex in K. And let's just assume, so for simplicity, we will assume that C is just a single word of length n plus 1. Because it's an n-dimensional simplex, so its length will have to be n plus 1. It's a word. We have to use a word because we're working with oriented simplices, so they're represented by words. They're just... Okay, so let's write, okay, so write C as, so it's a word. So you have a letter, let's say A0, A1, A2. Well, I should not put the comma. It just continues AN, where each AI, and I'll write it like this: the singleton set containing it, that's a vertex, right? You want to say this is geometrically, we would think of that as a vertex. So that is a vertex that is in our complex, because the set containing all of these is in the complex, and so the subsets of the set are in the complex. So in particular, every one of these individually, the singleton sets are in the complex. So you can think of these as like the vertices in the complex. So this is the, let's say C, your chain, your oriented chain is this. And then we define partial C as, and it's done the same way, where you basically make one of these vanish one at a time. So you first make this one vanish, so it would be A1, A2, AN, and then you alternate. Then you do minus, because this is an oriented, there's going to be an oriented sum. The next one is you're going to keep the 0th one, and you make the middle, not the middle one, but you make the A1 vanish, so this will be A0, A2, AN, plus so on. And if you want to write out, maybe to make it a little bit nicer, if I underline these so you get to see the actual words, these have to be taken all together. And if you want to write it out maybe a little bit more elegantly, the way people write it is you take the word A0, A1, AI minus 1, AI plus 1, AN, and they put this symbol over it. That symbol just means you leave out. This means you leave out that. You leave it out. And then it's minus 1 raised to the I. I goes from 0 to n. So that's the way you define the boundary operator. It's actually easier to define the boundary operator in this combinatorial sense because you have no maps to deal with. So it's just this formal sum of words. As you can see, by removing one of these letters, you lower the dimension and you keep the orientation of the letters the way that it is. So to show you an example, so here's like a very simple example. Let's say our word is just AB. So this is our simplex. So maybe what I'll do is, let me call it sigma, abusing notation a little bit, because technically sigma is not the oriented simplex, it's just a simplex, but let's just call this sigma. So you start at A and you go to B, you go like this. So sigma is something in C1 of your complex. I'll just write C1. I'm not even going to bother to write the complex. So this is something that's a one-dimensional chain. When you do the boundary of sigma, then here's how you do it. You drop the first letter, so you would just have B, and you do minus. Well, let me take it back. It's not the first letter. This is the 0th letter. This is the 0 position, and that's the 1 position. So you're dropping the 0 position. That's an even number, and when you drop an even number, it's a positive sign. When it's an odd number, it's a negative sign. So this is negative, and it's negative. You drop this one, so it's going to be B, and you end up with B minus A. And how do you visualize this B minus A? Well, it's just the endpoints. So the boundary would be this one with a positive and that one with a negative. So the boundary are the endpoints of that segment, and you have a plus or minus on that. And when you visualize it like that, it kind of makes sense. Like those definitions, they make sense. That's kind of the whole point for how the idea for why the definitions are made the way that they are. And then you have, let's say we have another one. Let's say sigma is a two-dimensional simplex, ABC, that goes like this. ABC. So then what you would do is the boundary of sigma. So as before, you start counting at 0, so 0, 1, 2, when you drop the 0, when you're left with BC, so you're left with BC. When you drop 1, you're left with A and C with a minus sign. And when you drop 2, you're left with AB with a positive sign. So this is now a formal sum of one-dimensional simplices. And in the picture, BC, so that would be BC over here. So you would, I mean, it follows, as you can see, it actually follows this. So BC, you go like this, AC. Now, this over here is AC, but it's negative. So that means you can, if you want to, you can replace this by CA with a positive sign. Because now you're going like that. Negative AC and CA are equal in the group C1, right? This is the group of oriented simplices. So this oriented simplex is equal to that one. So it's CA and then AB. So there you go. So that would be the boundary. That would be the boundary of this two-dimensional. This, of course, I guess I should have indicated this is a two-dimensional simplex. And the orientation is that the thumb is facing towards you. So when you use the right-hand rule, that's the side that faces towards you, and the right-hand rule calculates for you the boundary as you go around. So that would be the boundary. It will consist of 3 one-dimensional oriented simplices. So that's the boundary operator, and that's how it works. And more generally, this is how it works for any dimension. It just gets more tedious to write out, but that's how it works. And as before, this is not very difficult. You can do this yourself. Write this as a proposition. So if you have a boundary operator from Cn plus 1, let's say, of x, not of x, of a complex into Cn of a complex, and then you have another one from Cn of the complex into Cn minus 1 of a complex. Maybe if you want to be careful, you can decorate this as delta n plus 1, delta n, but we usually do not write that because we can figure out from context which one it is. So if you do this one followed by that one, then you're getting a map from Cn plus 1 from these chains to those chains, and this is the 0 map. This is the 0 map. So if you compose it twice, you get the 0 map. So all of these get sent to that. So you say that d squared is 0. That's the way you write it. And you say the boundary of the boundary is 0. And by 0, we mean there is no boundary. So if you have any chain whatsoever and you calculate its boundary, then you get a cycle. Okay, and now with that, we can define what we mean by homology. So Hn of a complex, this is going to be the group. Now it's going to be a group simply because when you're working with chains, you're using formal addition. If you have 2 chains, then you can automatically add them together formally. So that's why it's a group. It's a little bit different from the homotopy group. With the homotopy group, we define this operation called juxtaposition, where you move along one path and then another path. But in the homology groups, we start with the paths as representing our generators, and then you're just formally adding them together. So that's why you get a group out of this. So this is going to be the group of all n cycles in K. What do we mean by an n cycle? Just to make sure we understand this, these are going to be oriented n chains with no boundary. That's a n cycle. So this is the group of n cycles mod some equivalence relation. And what's the equivalence relation? So this is the equivalence relation. So we say that C1 is equivalent to C2. So these are n cycles. So we're defining what it means for them to be equivalent if and only if their difference, and all what the difference mean, this is just a formal difference. This is a list of n chains, this is a list of n chains, and you just take these 2 lists and you formally subtract them together. So it's just formal subtraction. So these 2, if and only if, so you want to say that this is homologically trivial, So that would mean that their difference is the boundary of something else. This is the boundary of K, maybe lowercase k, for some lowercase k that is one dimension higher. You can find an oriented n+1 dimensional simplex sitting inside your complex whose boundary will give you that difference. So that's the equivalence relation that you're introducing here. Now, if you want to be a little bit fancier, you can say, going back to our definition, this is the fancier version. You go back to Cn of k. There's a map, which we call delta, that brings you down a dimension. And then there's a map before that, that's from one dimension higher, which you're calling delta again. Technically, they're different maps, but they're defined in a similar way. And then the homology group, the nth dimensional homology group of this complex, you're going to look at the kernel of delta because you're interested in the cycles that go to 0. So it's going to be the kernel of the first mapping. So it's all about the homology group over here. It's in the middle one. So to get the middle one, you're going to look at the kernel of the first mapping. So this is the kernel from Cn, from this one into that one. And then you're going to mod it out, right? This is a subgroup. So this is what the kernel, this is now a subgroup of that. So you're going to look at the subgroup of that. These are the cycles. So you have the chains, and the cycles is a subgroup of that. So you look at the cycles, and you're going to mod them out by a subgroup. And the subgroup is exactly the ones, you see, those are exactly the ones that come from the previous dimension. So there's something in the previous dimension that maps to it. So you're going to look at the image group. You're going to take delta, you apply that, and you look at the image. So this is going to be modded out by the image group. It's the image of Cn+1 of k into Cn of k. Like this. And that's the way you define it. So you can see it's actually simpler to define homology for a simplicial complex than it is for a topological space. And it's also simpler in the computational sense that each of these groups is finitely generated. In fact, this is a free abelian group. This is a free abelian group. This is another free abelian group. And all of these are abelian groups with a finite list of generators. So this would mean that maybe the group in the middle is isomorphic to z to some power, let's call it b. And maybe the group on the left is isomorphic to z to the a to some power. And the group on the right is isomorphic to z to the c to some power. And you have basically mappings. You're mapping z to the a to z to the b, and you're mapping this to z to the c. And you're going to calculate the kernel of this mapping, the image of that mapping, and the quotient is what's going to give you the homology group. So that's the way it's defined, and it's computable because these are finite. These are finite copies of z. It's the way we set up homology for a topological space. It's not exactly computable. There's just too many generators to even work with. So that's the definition. And now that we have the definition, let's actually work through some examples and do these calculations. Let us do the following example. Our complex is going to be given by AB, AC, and BC. And as we remarked, we often do not write out every simplex because the moment I give you a simplex, we also know that its subsets are also included. So just to save writing space. And the way we visualize the simplex is we have 3 points. We have AB, BC, AC, and this suggests that the geometric realization of the simplex is homeomorphic to the circle. So in a way, what we're doing is we're calculating the homology of a circle. We're going to compute the homology. So when we say the homology, we mean Hn. Now, we're not going to write S1. This means this is the homology of the topological space. Rather, we will replace the topological space by a simplicial complex whose realization gives you the topological space. Now, there are a number of questions that one should immediately ask. The first of which is, how does one define realization, and how do you show it's homeomorphic with the circle? And then a more important question to ask is this group really isomorphic to the other group? So this is combinatorial, this is topological. Do the two approaches of homology coincide and give us the same answer? And this is something we'll discuss next lecture. How do you use something like this, the simplicial approach, to help you calculate the topological approach? But you can anticipate that the answers will be the same, and therefore let's just focus on this. We do not know yet how to calculate the homology of the circle, but we do know how to calculate the homology of this simplicial complex. So here's the way we do it. So we're going to calculate the homology group for every n. So let's start with H0 of this simplicial complex and ask, what kind of a group is this? Now, if you've done the homework problem on the zeroth homology, you would say that by looking at the picture, this is a simplicial complex which is connected, and therefore the zeroth homology will give you the number of path components. So there's only one path component, and so we would guess that this should be isomorphic to one copy of Z because you only have one path component. But let's carefully go through the definitions and see why that is how it works. So to calculate the zeroth homology, we start with zero chains. And then we will have, so you have to look at the preceding chain, C1 of K. And then you have the following chain. Now there's nothing that goes after C0. That's the beginning of this chain complex. So we usually just put 0 at the end. 0 just represents this is just the zero group. And this map, this is the boundary map. And this mapping, you can call it the boundary map again, but it has to be the zero map, the map that maps everything to 0. Now, C0 of K, these are going to be zero chains in K. And what is a zero chain? A zero chain is just a point. So these are the singleton sets that make this up. So there's 3 of them, A, B, and C. So C0 as a group, it would be generated by A, B, and C, and then you have arbitrary coefficients. So let me write it like this: N1A plus N2B plus N3C. So it's all linear combinations where the coefficients are allowed to be integers. Okay, so that's what it would be. Now, there's not really much to say about orientation here because this is just a single letter, so there's not much else to do with it. When we talk about one chains, you'll see how the orientation comes up. But these are just points, and it's the free group. So you have these 3 points, and then you have all possible combinations because it's the free group generated by these 3 symbols. And this group is, of course, isomorphic to Z cubed, right? This is one copy of Z, right? This is an arbitrary coefficient. So this is isomorphic to Z cubed as a group. Now, how do you find the 0 cycles? Well, this 0 map, it's sort of like your boundary map. And so if you choose a 0 chain, it's automatically a 0 cycle. So every 0 chain, so N1A plus N2B plus N3C, is also a 0 cycle. So to check it's a cycle, you apply the boundary map. Well, there is no boundary map, so it's just automatically 0. So it's automatically a 0 cycle. And now the question comes up is, we need to identify. So thus, the zero homology group of this complex will consist of all 0 chains mod some relation. There's going to be some way of relating them together and saying they are the same. So it would look like this, but you need to have some kind of relation. And the way you do it is, so you're going to observe that A and B are equivalent to each other. So these two zero cycles, they're equivalent to each other. Why? Why? So the question is, can you find a one simplex whose boundary will give you their difference? That's what you're asking. If two cycles are equivalent, it means their difference, by definition, is the boundary of a simplex of a chain of one higher dimension. So can you find a one-dimensional chain which will give that to you? And the answer is yes. Yes. The boundary of BA would be A minus B. So this is the oriented simplex. This is the simplex that contains these two letters, and it's oriented that this is first and this is second, and then its boundary is the endpoint minus the beginning point. And as you can see, you get that. And the reason why you do that is because BA is in the complex. So if you look at your complex over here, you can find BA. If it was not in the complex, then you're not able to do it, but it is in your complex. Okay, so the boundary would be that. And likewise, A is equivalent to C. Okay, so thus, if you have any zero chain, N1A plus N2B plus N3C would be equivalent. You can just replace this all by A. So you have N1A plus N2A plus N3A, and so you get that this is N1 plus N2 plus N3 times A. And what we see from here is that A is the generator for the group. So thus, I mean, in the end, this is just some integer multiplied by A. So thus, the zeroth homology group of this complex, all of the zero simplices, they're classes, they're homology classes. So they're all determined by the homology class of A times some integer n, where n is an integer. But if you look at what this is of course the group. I mean, this is just a group that's isomorphic to the integers. So this is the class that generates the group for you. So there you go. The zeroth homology group of this complex is isomorphic to the integers, which is what we anticipated before we even solved this problem. Now, before we do H1, let's do H2. So what is Hn of k for n bigger than or equal to 2? And this group is just the zero group. So why is that? Well, let's just do it for 2, and then the same kind of argument will work for any other dimension. Because to find H0, to find the second homology group, you're going to start at C2. You're going to start with two-dimensional chains in the complex. Then you're going to consider the boundary map going into one-dimensional chains, and then you will consider the boundary map from three-dimensional chains. So you have to find the kernel of this and the image of this. But what is this? This is, if you just write it out, this is just going to be the group generated by two simplices. Maybe we should say oriented two simplices in K. But if you look at our complex, right, what is our complex? Our complex is, well, as a picture, it's just this. Notice there is no two-dimensional simplex. That's not part of this complex. So you could say it's the empty set, but the convention here is to interpret this as the zero group. So this is just the zero group. And now it's very easy to find the homology, because the homology will consist of all two simplices that are cycles. Well, there's only one of them, and that's just 0. So thus, the two-dimensional homology of this complex is the 0 group. And the exact same argument works for every higher dimension. Now, the most interesting one of all is the first homology. So let's do that one. So the first homology would be, so let us find the first homology of this complex. And to find that, we start with one chains, we map them into 0 chains, and the previous map is from 2 chains. Now the 1 chains will consist of all one-dimensional simplices that you see. So yeah, the picture is again this. So as before, this group is isomorphic to Z3. And it would be generated, I'll just write it like this. It's generated, well, maybe I should not write that. I'll write it like this. It's the set of N1A plus N2B plus N3C, where the coefficients are integers. C0, oh, I see, I already made a mistake. Okay, so that's actually C0, so sorry about that. So this is actually C0. So yeah, so let me get rid of this. So C0 would be this. It's what we had before, where the coefficients are integers. And this one would be generated by all 1 simplices. So you have to find the 1 simplices, but when you write down the 1 simplices, you just choose an arbitrary orientation. The orientation does not really matter, you just pick one. So let's say you go from A to B. So you can have, let's call it M1 AB plus M2 AC plus M3 BC, where the coefficients are integers. Okay, so the coefficients, these are integers, and these are just the formal objects that make up the group. Now you will notice I'm writing AB. The reason why I'm not writing BA is because the convention is that BA is negative AB. That's what we mean by oriented simplices. So you do not repeat them again. Okay, so you just only write that out. And then for 2-dimensional simplices, well, that's just going to be 0. That's just 0. So to find the first homology group, what we would need to do is we have to ask the question, which, so first find the 1 cycles. So let's say we choose, so to find the 1 cycles, we first pick a chain, a 1-dimensional chain. So this is a 1-dimensional chain. Okay, and now we're going to check. So we're going to ask the question, when is it a 1 cycle? So we have to apply the boundary to that chain. And we would get, so the boundary acts distributively on these words. So you're going to apply the boundary operator on each of those words. So you will have M1, then you have B minus A, plus M2, C minus A, plus M3, C minus B. And now if you reorganize it, the coefficient on A, it would be negative M1, negative M2. The coefficient on B will be M1 minus M3. And the coefficient on C would be M2 plus M3. And we want that to be equal to 0. Well, in order for this to be equal to 0, you have to understand that A, B, and C are generators. They're basically like a basis for the group. It's a little bit different because I know you're probably used to talking about vector spaces and a basis for a vector space, but this is very similar. It's almost like a vector space. This thing over here, this is almost like a vector space. We're saying it's isomorphic to z to the 3. The only distinction is when you deal with vector spaces, you talk about like r to the 3 or r to some other dimension, and the coefficients in front of the vectors happen to be real numbers, but here the coefficients happen to be integers. That's really the only distinction. But these are the basis elements. And likewise, this one over here, this is also isomorphic to z to the 3. And these are the bases, these simplices, A, B, and C, those are your basis elements. So in order for it to be equal to 0, this is the formal 0. This is the 0, that's the formal 0 among one-dimensional chains in this complex. The way that is achieved is by setting all of these equal to 0. So now if we set it equal to 0, here's what we have. We have minus m1 minus m2 is 0, m1 minus m3 is 0, and m2 plus m3 is 0. And now we have to, that's basically like a linear system that we need to solve. So it's up to you how you want to do it. Maybe we set it up in matrix form. So this is sort of going to be like m1, m2, m3. So the coefficient on m1 is -1, -2, 0. This is 1, 0, -1. That's 0, 1, 1. And now you can ask Wolfram to row reduce that for you. Well, okay, let's not be too lazy. So let's change negative signs, make it 1, 1, 0, 1, 0, -1, 0, 1, 1. And now we can subtract, we can, I guess, you subtract this, or maybe what I should have done is, I should have just put this one in front. So 1, 0, -1, -1, -1, 0, 0, 1, 1. And then you add the first row to the second row, 1, 0, -1, 0, -1, 0. As you can see, this is kind of boring. The topology is interesting, but the computation is boring. Normally, you can just do this on software. And then we go again, 1, 0, 0, 0, 1, 0. And then we subtract it away like this. And we go again, 1, 0, -1, 0, 1, 0. We subtract the second row from the third row, that's 0, 1. And, oh, okay, I made a mistake. Okay, this is, I forgot to add an extra, look at that, I forgot to add an extra row of zeros. So how about instead of, let me just do it differently. I'm trying to be too algorithmic here. Let's just look at this one. M1 is equal to M3, okay? That's it. And then this one tells us that M2 is equal to negative M3, and M3 is equal, yeah. So thus, the zero, not the zero chains, the one chains have the form. So the M1, you see the M1 coefficient is M3. So in general, we were talking about M1 AB plus M2 AC plus M3 BC. So replace M1 by M, so this is just M3. M2 is negative M3. And in the end, we have M3 multiplied by AB minus AC plus BC, which we can rewrite as M3 AB plus CA plus BC. Okay? So this shows, so the group of one-dimensional chains is equal to, it's equal to M3, I'm just going to write M, multiplied by the following cycle, where this coefficient is an integer. So in particular, this group is isomorphic to the group of integers, because that's the cycle that generates it. And the next thing that we need to do, we then need to mod out by the image of C2 of K. Because we have to, when you calculate the homology group, you have to determine which of these 0 cycles are trivial, homologically trivial. Because the way this works is you first get the kernel, which gives you the cycles, and then you look at the image of this map, which tells you the equivalence relation. But this is 0. So the only ones that are homologically trivial is just the 0 cycle. And then we would write that since is the 0 group, it means the only one cycle that is homologically trivial is just the 0, 1 cycle. So that means there's no need to put any equivalence classes. So hence, the first homology group of this complex is, the first homology group of this complex is therefore equal to, so it's the set of homology classes. So this is the generator for the homology class. So you would say it's class generated. Well, I meant to say this is the homology class of this, which is just itself, because it's only equivalent to itself, as we've said. So this is what we have. Now in the picture, A, B, C. So in the picture, we're doing this. We're going like that. That's AB. Then we have BC. And then we have CA. So look at that. Okay, so basically, I made a small mistake here. I meant to say H1. So basically, the first homology group of this complex K is isomorphic to Z, and it is generated by the one cycle that winds one time around the triangle. This should be very reminiscent to when we talked about the fundamental group of the circle. But the fundamental group measures something a bit different, but it's very similar to that, right? You kind of wind one time around it, and then the homology group is then generated by that cycle that goes one time around. So look at that. We calculated the homology of this fairly simple complex. And then you can go ahead and look at other examples. So let's look at an example that involves the tetrahedron, the surface of the tetrahedron. To find the homology of a tetrahedron, we describe the simplicial complex first. So this would just be the complex consisting of so it will go like this. It will go ABC, ABC, ABD, and we have ACD and BCD. So we have 4 simplices of dimension 2, and of course we're not writing down all of their subsets, but that's understood. And then we have a figure like this. This is A, B, C, D. So that is our tetrahedron. That would be the geometric realization of that complex. And say we want to compute the first homology group of this complex. How would we do it? And we're not actually going to compute it in this lecture. What we will do is we will set the problem up. And then in the next lecture, we will discuss the computational issues that arise when you're trying to do this. Normally, one would do something like this using software because doing this by hand would be tedious. But let me just set the problem up, and then we will continue with this next lecture, and we will also show how this is related back to topology, how this is related to the homology of a topological space. But first, what we'll do is, if we're interested in the first homology group, we go back to the chain complex. We have one that goes into C0, and then we have one that goes into that comes from C2. And we have a map delta, and we have a map delta. Now, as we remarked, these are going to be isomorphic to a certain number of copies of Z. These are the zero-dimensional simplices, which would be the vertices. So this would be Z to the 4. The two-dimensional simplices would be the 4 faces. So this is Z to the 4 again. And the one-dimensional simplices, well, you can count them, but the fast way to do it, this is really 4 choose 2. So that would be 6. So that is Z to the 6. So we're mapping Z to the 4 into the Z to the 6, and we're mapping Z to the 6 back into Z to the 4, and we have these maps. Now, this will be very similar to what you do in linear algebra. Then in linear algebra, these are usually the real numbers, and these are linear maps. But these are group homomorphisms between abelian groups. And if you are familiar with the language of modules, these happen to be modules over the integers. So they're basically like vector spaces, and these deltas are going to play the role of linear maps. Now, to describe, so go back to linear algebra. So maybe this would be helpful. So let's say this. So in linear algebra, you can represent a linear map between two vector spaces as a matrix after you choose bases for the two vector spaces. So you choose, so basically the way it works is you have some linear map between two vector spaces, V1 and V2. You find the basis here, you find the basis there, and then you observe how the linear map acts on the basis elements. So each basis element, when you apply F to each basis element, it gets mapped over here, so it gets written out in terms of those basis elements, and that's how you get the matrix representation for your linear map. So this is actually almost the same thing, except we're working with the integers. So to see how to do it is we need to find the basis for these. So let's write the basis for this one. So the basis for this one would be A, B, C, and D. This is the free abelian group that's generated by these vertices. So this would just be, the basis here is A, B, C, D. So you choose an order to your basis. So let's say this is the way you do it. Then you need a basis for this one. So these will be one-dimensional simplices. So there will be 6 of them. So this can be AB, AC. Maybe we'll write it like this: AB, AC, AD, BC, BD, CD. So there's 6 of them. And then we have a 4-dimensional basis for this one, and that one will consist of 2-dimensional simplices. So this would be ABC, ABD, ACD, BCD. So those are the 4. And now to determine, so these are group homomorphisms, and you want to sort of write it in terms of matrix notation. So in matrix notation, you're mapping Z to the 4. So you're going to basically have a matrix. So you're going to have some kind of matrix over here, A, and you'll have some matrix over here, B. So A would be a matrix that will have 6 rows and 4 columns, and B will be a matrix that will have 4 rows and 6 columns. So because A is going from 4-dimensional space to 6-dimensional space, so the matrix is from 6 to 4. So that's the way it gets set up. Now to actually find what this matrix is, so this is going to be 6 by 4. So 1, 2, 3, 4. So maybe that's not the way I want to do it. So I'll do it like this. So we have 6 rows. 1, 2, 3, 4, 5, 6. And then we have four of these. And we're going to fill these in with numbers. So that's our matrix So it's a large matrix. So you can see this is somewhat tedious to do by hand, even for a tetrahedron. But now, to determine what this is, it's convenient to arrange these. So these over here, these rows would be the basis elements. So this would be AB, AC, AD, BC, BD, CD, and going across, you would have the basis elements for this group. So that would be ABC, ABD, ACD, BCD. And to determine how this looks like is, this is your linear map. So you're going to be applying delta to each of these basis elements. So you apply delta to the first basis element. Now, I'm going to do it for just one of them. So let's do it over here. Delta apply to ABC. So when you write it out, so you're going to drop the 0th one. So you have BC. Then you have minus, you drop the one in the first position, AC. Then you drop the last one, so that would be plus AB. So that's the way you write it out. And this is going to be written out in terms of the basis element. So now you see the coefficients here is you have 1, -1, and 1. So those are the coefficients in terms of the basis elements. So now you just have to put it in. So BC would be 1, AC would be -1, and AB would be 1. And now that you see how it, and all of the other ones are going to be 0. And now that you see how it works, you can kind of see what the idea is, that the one that's negative is when you take the 2 on the outside. So if you take the 2 on the outside, that's going to be with the one that's negative. So this one is going to be -1. This one AD, so that would be this one is also -1, right? ACD, the ones on the outside, -1, and BD, that would be right there. And now you get the 2 adjacent ones, AB, that would be 1, and BD, that would be 1, AC, that would be 1, and then CD. And then BC would be 1, and CD would be 1. And the rest of the remaining numbers are going to be 0. So this is basically what you've created. You have a map from Z to the 4 to Z to the 6, and the matrix, so the linear map is represented by a matrix, which is all of this. And then you have a matrix B over here. Let's write over here the matrix B. So this is 4 by 6. So let's write over here B. So this is 1, 2, 3, 4, 5, 6. And you have 4 of these. This one's going to go a little bit differently, but it's the same idea, that the numbers going across the rows will be your basis elements. And the numbers going down, these would be the basis elements over here. So A, B, C, and D. And now you apply the boundary operator to each of this. So let's do it again for the first one. So you will have the boundary operator applied to this first basis element AB, and it would be B minus A. So that's the way you do it. So notice you have B is with 1, and A is with -1. So the pattern is the first one is negative and the second one is 1. And with AC, this one is -1, and this is 1. AD -1, 1. This one is going to be -1, 1. That's BD, so -1, 1, and then this one is -1, 1, like this. So that's how it works. And to find the homology group, so to compute the homology group of this complex, which, I mean, you should see that this is fairly tedious because you have fairly large calculations one has to do. The earlier example that we did with the triangle, that one was so much simpler, but this one is, you can see clearly more involved. You have to find the cycles. So you find the cycles by taking the kernel of B. So you're going to look at the kernel. So B is a linear map from Z6 to Z4. So you're going to find the kernel. In the language of linear algebra, perhaps you recall that's what you call the null space. And then you're going to quotient it out by all of the boundaries of two-dimensional simplices. So you're going to have to take the image of this map, linear map A, that goes from Z4 into Z to the 6. And calculate what that is. So perhaps you recall in linear algebra that when you have a linear map and you map one space into another space, so there you're talking about vector spaces, and you talk about the image space, you often talk about this thing called the rank. But this is going to be a little bit different from what you're typically used to in a linear algebra class, but this is just a setup to how one does homology. And this is something we will discuss in the follow-up lecture. Really, the purpose of this lecture is just to do a different theory of homology, which is the homology of simplicial complexes. So it has a very combinatorial feel to it. And what remains is to show what is that connection between topology and combinatorics, and furthermore, what is the effective way to compute this. So maybe to summarize, to compute, so computations of simplicial homology come down to computing the following problem. So you have Z to the A being mapped to Z to the B, being mapped to Z to the C, and then you have some matrix here A, some matrix B here, and you're going to assume that BA is 0. This is just a composition. So A goes first, B goes second. So it's like doing the delta, the boundary map twice is 0. And you want to calculate the kernel of B modded by the image of A, right? And this is going to give you homology. So we're going to discuss how to do that. So the good news is that there's an algorithm for doing this. And this is something that we will discuss. And so in theory, you will be able to do this for any simplicial complex. Of course, once the simplicial complexes get very large, then it becomes more computational to do. But at least in theory, you can always do something like this. So that's something we'll discuss in the next lecture.